you look at this first problem here, you've got a hardware store that orders a shipment of 2 types of hammers for $168. One type of hammer costs $3, the other type of hammer costs $5. If the store ordered 40 hammers in all, how many of each type were ordered? If we're asked to solve this particular problem using a system, if we're asked to set up a system to solve it, then we need to define a couple of variables. Now, how you define those variables are up to you. We use X and Y a lot. Obviously, when we solve systems, you want to be consistent, use X and Y all the time, that's fine. If you want to be a little more specific to the wording of the problem, we're talking about hammers here, you want to use an H, that's fine. What I decided to do on this one is I considered how I would set up my system. I know there's 2 types of hammers involved, so I use the variables A and B. For A, I let that be hammer 1. For B, I let that be hammer 2. There are my 2 types. Okay, so from here, we need to start including the values that are given within the problem. We need to come up with 2 equations that relates these variables we've defined somehow. And, a couple of things that stand out to me. I don't know what the total number of each type of hammer is. I just know that A and B represent that. I do know that A and B, if I added them up, would equal one of the values that's given within this problem. It says the store ordered 40 hammers, right? So if I add these up, there's an equation I could use where A plus B would equal 40. But then another equation that's pretty common on these problems to set up has to do with some kind of value, like in this case, money value. We know that in total here, there's $168 worth of these hammers. And we know that one type costs 3, the other type costs 5. So if we knew that we had a certain number of hammers here for the first type, and say that went with $3, then 3 times A would give me that total amount from that piece. And for the second type, if we let the $5 go with the second type, then take 5 times that second type, the number for that second type. That would give me the total for that part. If I add those together, I get 168 overall. So the way I set up this system, define a couple variables first, set up one equation that has to do with totals and another equation that has to do with basically the money amount. Once you get your system set up, you're all set to go. You can use any method you want to solve. For me, I went with elimination. I decided, I could get rid of what I get rid of. I got rid of the B's. To get rid of the B's here, I'd multiply this top equation by -5. If I do that, I get -5A minus 5B equals -200. Second equation stayed as is. So now if I add through the 2 equations, I know the B's are going away. I've got -2A left equal to -32. Divide by -2, A equals 16. So for that first type of hammer, the amount of those hammers that I have based on this problem, there's 16 of those hammers. To figure out B, well, we know with a system as it's set up, we can go back to one of the equations that we originally set up, plug back in what we know. We know A is 16. So if I go back to this first equation here, let A be 16. Well, it wouldn't be too hard to figure out B, right? It'd be 16 plus B equals 40. Subtract 16 over, and B is going to be, in this case, 24. So you got 24 of the other type of hammer. Again, go back to the question. It says how many of each type were ordered. Got to make sure you're answering the question. You got 16 of the first type, you got 24 of the second type.
Take it easy.
All right, on the second one, it says with a given headwind, a certain airplane can travel 3,500 kilometers in 7 hours. Flying in the opposite direction with the same wind blowing, the airplane can fly the distance in 2 hours less. Find the airplane's airspeed and the wind speed. Okay, so it's asking us to find two things, talking about the airplane's airspeed and the wind speed. It would make sense to designate variables around those two ideas. So we could let A equal the airplane's speed, understanding it's the airspeed. And we could let, if we want to be a little more specific here, W equal the wind speed. So define a couple of variables. Now, using those variables, let's set up a couple of equations to set up ultimately our system. If you break this down, we're talking about some distances, we're talking about some times, we got some speeds thrown in there that we want to find, right? This is a classic distance equals rate times time scenario. So if I use that type of formula as my inspiration here to set up some equations, let's go back to this distance here. Distance is 3,500 kilometers, right? So 3,500 would equal, let's see, what else do I know? Initially, it's talking about this headwind and how we're able to travel this in 7 hours. When we talk about a headwind, what are we talking about? Okay, the wind's blowing at you. The wind's against you, right? So if you want to figure out how quickly the plane's going, you got your speed that represents the airplane here. That wind is blowing against you. So the speed of the wind, we would subtract. That little quantity right there represents my rate. The airplane speed with the wind blowing against it. So we subtract away. Now if I multiply by 7, 7's that time, right? So if that makes any kind of sense, trying to set up a second equation now, on the second equation, following this model of distance equals rate times time, does the distance change? No, it's still 3,500. So 3,500 is going to equal, what else they give us here? It's talking about the airplane flying in 2 hours less, right? So 5 hours. We know that's going to go at the end here. But that's going to be flying in the opposite direction with the wind blowing. So the wind's helping, right? So you were flying into the wind, you had to take it away. Now if the wind is helping, you're going to add it on to that airplane speed. If you use the distance equals rate times time model, you can set up two equations here, where if I, well, clean this up a little bit, let's distribute the 7 through in the top equation. I get 7a minus 7w equals 3,500. Multiply 5 through in the second equation, get 5a plus 5w equals 3,500. You know, if you guys are okay with elimination, we could use that again here. When I did this, I eliminated the a's. So in eliminating the a's, it would make sense then. Got a 5 down here, so let's multiply a 5 to the top. And then I've got a 7 here. Let's multiply a 7 to the bottom. Need some opposite signs though, right? So I need to make one of these negative. I'll make the top one negative. If you multiply that negative 5 through the top equation, you get negative 35a plus 35w equals, let's see, what is that? If you multiply, you get negative 17,500. And then adjusting your second equation, you got 7 that you're multiplying through, so you got 35a plus 35w equals 7 times 3,500. That'd be 24,500. Stacked up, ready to go. A's cancel out. You're left with 70W equal to, this would be 7,000. Divide by 70, and W, which represents that wind speed, is going to be 100. So in this case, if you threw a unit of measurement on there, it'd be 100 kilometers per hour, right? With applications, we can always do that. We can always throw some units back on there. But wind speed, 100 kilometers per hour. If you want to figure out the airplane speed, because we are asked about that, right? Find the airplane's airspeed and the wind speed. Well, go back to one of your equations here. Plug in W as 100. So if I go back to one of my equations, maybe this one right here, maybe one of them up here, right? Doesn't matter. But let's take this one right here. Plugging in W as 100, I've got 5A plus 5 times W as 100 would be 500 equals 3,500. Subtract 500 over. Got 3,000. If you divide by 5, then A is going to be 600, right? So the airplane's airspeed is going to be 600 kilometers per hour. All right, and in trying to identify what kind of problem we're working with, and considering the first two that we work, let's see if there's any consistency between this problem and those first two. You got a grocer that sells pecans at $1.20 a pound. You got peanuts that are being sold at 70 cents a pound. If he's selling 50 pounds of nuts for a total of $50, how many pounds of pecans and how many pounds of peanuts did he sell? So you identify a couple of variables, or define a couple. You could have, say, P be peanuts, and I don't know, can't use P again for pecans. I'm going to use G because honestly I think pecans are gross. That's just me personally. So G for pecans. A lot of people like pecans. I'm not a fan. Okay, setting up a couple of equations here. Knowing that P represents the total number of peanuts, G represents, excuse me, the total number of pecans. Talking about totals here. Any totals within this problem, any number totals within this problem that maybe we could use here to set up an equation? Anything stand out? 50 pounds, right? Because remember, these are all being measured in terms of pounds for a total. We could take P, the number of peanuts, plus G, the number of pecans, let that equal 50. Now, we have a total money amount here, right? A total of 50 bucks. And we happen to know per pound what each of these is worth. So for the peanuts, those are 70 cents a pound. Take 0.70, multiply to the peanuts. For the pecans, that's $1.20. So 1.20 times G. That equals 50 bucks. If I threw a decimal in there, right, 0.00. Now here's why I threw the decimal in here, and this is what makes this problem semi-unique compared to the first couple that we've worked. I mean, really setting this up, this is a lot like that first problem, right? But what makes this a little more unique is that decimal place. It'd be nice to get rid of those decimals. So since these decimals are all being held by the same number of digits, we could drop the decimal out. Just to understand, in theory, what you're doing is you're multiplying everything by 100 when you do that. If you multiply everything by 100 in this equation, that's going to drop that decimal out. So I start by removing the decimals. If I do that, let me bring this down here. I've got 70p plus 120g equals 5,000. I've got my other equation of p plus g equals 50. Now, just to give us some variety and also a good way to review, let's do substitution on this one. Elimination works, we know that, but let's do substitution. Let's, I don't know, let's solve for g here. You solve for g, g is going to equal 50 minus p, right? So I'm going to take 50 minus p, insert that in the place of g up here. So I get a new equation to solve where I'll be able to solve for p. That's the number of peanuts in terms of pounds. All right, let's get ready to crunch some numbers here. If I distribute that 120, I've got 70p plus, you got 120 times 50, which would be 6,000. You got 120 times p, 120p, equals 5,000 here. If you combine your like terms, put the p's together, we got negative 50p. I'm going to subtract that 6,000 over. Got negative 1,000. P then is going to equal, when we divide both sides by negative 50, how much? $200? Now, you said 200. Is that right? Here's a good lesson right now. These answers are supposed to make sense, right? I'm not saying 200 doesn't make sense. But what happens when you go back to figure out g? You go back and figure out g, you plug in 200, right? And you get a negative amount. So that's a good indicator that maybe we made a mistake. It's not 200, is it? It's 20. I'm glad we did that just so we can demonstrate the mistake. It's 20. So in terms of peanuts, we've got 20 pounds. In terms of the pecans, which was G, we've got 30, right? Because it'd be 50 minus P, so 50 minus 20.